you are anticipating to deal with NMR and EPR, then you need to have a picture what is going on with magnetization of material and what is being done, right? And there is magnetization coming from either electron spin or proton spin, right? And the magnetization coming from spin does have as a magnetization vector 3 projections, X, Y, and Z. And the users, the people who do not target quantum theory as a goal of life, but use it only as application, may need to borrow from there anything about any knowledge about how this magnetization vector changes in time. Okay, so we need to prove, and all introduction was done before, right? In the previous meeting. Three projections of magnetization, 3 projections of spin can move, and most typical motion is along the equatorial plane, and it is very similar to position and momentum for harmonic oscillator. So we just need to make an equation for a pedestrian walking on the equator. Okay, so the way to get this answer comes through a little surprise quiz that we need to finish about 5 minutes before the end. So I will provide all details so that you can do it. And your intellectual capacity is like 2 orders of magnitude above this quiz. You're able to do it. It's guaranteed.
That's a lot.
That's a lot.
What else? There will be 2 side nodes, but they may take substantial time. One side node is for melody, another side node for sound. So I will. What?
Feels a little scary to get to that slide.
I'll attract your attention when there will be this special
Yeah.
nodes. Okay, so we discussed this slide last time. The dots on this map sometimes can be connected because same theories are applied to 2 different subjects. This is something that you may remember from previous meeting, right? The spin can be represented as 2 expansion coefficients in 2-dimensional vector. And it was about to be shown in the middle of previous lecture, but we didn't reach to this point. I was just going to say that we have more material to go, and then I decided, no, Mary Rogers is not a good thing for the class. Actually, the scientists are peaceful. But I still need to go. So the harmonic oscillator does have equation and equation operator. The equation operator was used to derive eigenstate to show that you cannot jump lower than basement, and this operation will be 0. And analogous operators do exist for this 2-level system. You cannot jump lower than ceiling. You cannot jump higher than. You cannot jump higher than the ceiling. You cannot go. Yes. So the symbols here, S plus and minus. So in harmonic oscillator, one uses A and one puts dagger on the top. For spins, typically when people put it on the bottom. So if you assume that alpha was down and beta is up, then by S plus we flip from down to up, from S minus we flip up to down. And there is a thing. It works. Okay. And I'm writing blind. The screen is black.
Oh.
So if I do S plus 2 beta, it will be 0, because you cannot do creation higher than the top. If you do S minus 2, wrong.
Would it be 0 as well?
If you apply to Also, it will be 0 as well. Okay, now a little exercise that I suggest we do on the board. It may delay everything, but I think it is the best way to memorize things. So we come up with two. Here. And we do this with the camera. Okay. So 0, 1, 0, 0. 1, 0, 1, 0, 0, 0, 1. Yeah, we have 6. No, only 5. Then I will have 6. No. I'm checking the number of people in the class so that everyone gets a flavor of making a little bit of
Or else it's not responsive. I'm on there.
And one more exercise. Or maybe 2, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So here should be a matrix. Here should be 4 vectors. So you have a, because you're sitting so close, you have a choice to select whatever you like. Go to the board and write one of these examples. Melody, prepare. You will be the next.
Okay, I'm ready.
Okay, now interpret what how do you. That's correct.
Yeah.
So we can interpret this one. So if this was spin down, and this was S minus, that would be so that would be 0.
No, I don't like that.
Right, it's a little pathetic, but we should try. And then as a result, you go spin down. Yeah, thank you. That's correct.
My turn.
It is not complicated. It's much easier than things that we were doing through the several months. Yes. And how would you interpret it? Like S plus acting on the spin down. You get us spin up. Yes. Yeah, that's correct. Thank you.
Guys.
Patricia, your example will be, your and mine will be most complicated. Get ready, please. So find S plus to spin up will be 0, nothing. Yeah, correct. Yeah, thank you.
Are the S pluses and minus not switched from the way that they're written right now?
You will try to catch me. I will be absolutely wrong if you try to ask me which one is up, which one is down. So, Patricia, here is yours.
Oh,
I
don't know. It doesn't matter. It's all relative.
Okay, thank you.
That's
Huh?
right, yeah, that's right.
Okay, now, and the rest will be there, right? That's it. Okay?
Yeah.
So, the combination of S minus S plus will give an operator that projects only spin down. Combination of S plus S minus will give projection that parses only spin up, right? And another interesting observation, if we add them together, then S plus S minus plus S minus S plus will be equal what? This plus this will be matrix which has ones on the diagonal, right? So like unit identity operator, right? And for harmonic oscillator, we used to have a dagger A equals one commutation, right? Because it was minus between them. Here for spin operators, it is instead of minus, it is plus, right? And they call it anti-commutator. And there is a notation like S plus comma S1, and here one uses curly brackets. We are going to use this little trick in some derivation that we have plenty of time to complete. Hope it is yet a positive experience and you do not suffer yet. Okay. The kings of university.
Yes.
Insurance rate.
I'm sharing all that for the rest of my life.
He's a
Not okay.
gesture.
So you need this, and some people like up and beta more than up and down, but it's just matter of taste. The things that you did can be expressed in the Dirac notation. So going from beta to alpha, it will be S minus, and then one can look on the thing here, take the orthogonality relation, and then it will be only alpha. You see the logic, right? Okay. And if you do a product of two raising operators, it will be a thing that Patricia did derive for us. Here is the thing. So if we put factor one here and factor one there, so camera is not. Maybe I'll refocus because I'm going to show something. Okay. So if you put factor one here and factor there, it will be identity operator. You did prove it. One can put different numbers here. For example, one can put epsilon alpha, epsilon beta here, and then it will be a matrix with values epsilon alpha and epsilon beta on main diagonal. And why don't we call it a Hamiltonian? Right? So right now we are bound only to two-dimensional Hamiltonian for spin, but formally by designing a matrix which contains energies on main diagonal, it's as good as Hamiltonian. This is a special note for Melody, because in her project there are a couple of electronic states, maybe four, but one needs to design operators in this style. I'll explain what she's doing. So, continuing foundation for Melody's project. In Dirac's notation, so she does have molecule with ground and excited state potential energy circuits. Kinetic energy is the same for both of them, so it's multiplied by additive operator, but potential energy is different for one electronic state and for another electronic state. Okay, and this notation is the best way to explain what Melody is doing when she will be presenting her talk. For us simple guys who are looking on spin, what are the values of this alpha, epsilon alpha and epsilon beta? Don't spin up and spin down have the same energy. What do you think? Yes. In which case it is wrong. Discussion is the best part of the class. So spin up, spin down, same energy. Like if you have Aufbau in your freshman chemistry, 1s2, 2s2, like 2 means like spin up, spin down have the same energy. In which cases they will have different energy.
Would it be like if you're comparing from different energy levels, like you have one in the two?
When this energy levels will have different value.
Different order.
Yeah.
Like same orbital, like let's consider maybe bring additional electron to hydrogen atom. So it will be 1s2.
Oh, if it's like ionized.
No, we are fine with one electron. If you flip the spin of the 1s1 in the hydrogen, in which case energy of spin up and spin down will be different. What should we do? Which external perturbation? You all know. It's just my favorite game to surprise you by unexpected questions. No one of you is serving to the group of Dr. Ranguyan. But your advisor does have a tool in his lab that looks like a heavy metallic two thick discs.
2 thick, heavy metallic discs.
Yes. So once again, what should you do to spin?
Magnetized?
Some +5. So in magnetic field, in the magnetic field, spin up and spin down, you have different energy.
How?
5 is too many.
No.
No, it's not 5 or.
You all know it, right? So the needle of a compass has different energy. If you flip it opposite to the magnetic field of the Earth, it doesn't point because it will be different energy, right? So in magnetic field, spin up and down, split energy. And this is a main foundation of NMR and PPR, right? So the values of epsilon alpha, epsilon beta for spin will be proportional to the magnetic field. Like epsilon alpha will be minus magnetic moment times B magnetic field. Epsilon beta will be plus U times B, right? And 1/2 in the middle, in the factor, right? The stronger magnetic field, the stronger the spin. We are moving in the right direction. Yes, exactly. So, based on your derivations, we can build a dictionary. So, left column, middle column is something that you are very comfortable in, and right column is translation of the same things into Dirac notation, right? This is something that you need to complete your surprise quiz. So we will, and even it has lower right of the quiz has a copy paste of this diction. So even if there is a product of these operators, it will get a graph of 2 things: a projector and flipper, right? Okay. Now I will the rest arriving to the goal will take 10 minutes, but I will postpone it. I will make a comment for about 15 minutes. They're mostly directed to Sam, but you all will enjoy it. So the project that Sam is doing deals with Slater determinant that we briefly covered in the class, right? And there is a interesting thing that one can, instead of hypothesizing the antisymmetric wave function, one can get it as a literal mathematical solution of a problem with two spins. I will skip and make it quick, but it is a like side opinion, an additional foundation for Sam's project and source of how the it will be a path. I will not derive everything. It will be a path how a Slater determinant of antisymmetric wave function can be made. So we already get through this thing, right? Dirac notation for S minus and S plus, right? Generally, the wave function of a spin is two expansion coefficients in front of basis functions. Product with projector. It's not as important. If we do have, if you want to find expectation value of a matrix element, we need Bryant ket of the spin wave function, right? Spin and operator should be placed inside. So if you want to find an expectation value, and it is not the main thing, I will give warning to Sam and to all everyone in class when it will be major problem. Here is just another little foundation. So Melody and Eva were serving as a champion and coach in describing matrix elements. So here's the same thing, but in discrete way, right? Wave function, Bryant ket, and operator. If you want to find matrix expectation value of this operator for this quantum state, we just need to open brackets and two here, two there with 4 terms total, right? Yeah, we probably do not have time to do them on the board, but next year. So if we open the brackets, so C alpha star C alpha, alpha bra alpha ket. You're following, right? Then C star alpha C beta, alpha bra alpha ket, and operator is in between everywhere. Now, if we want to go further, we need to use dictionary and replace this algebraic abstract operators by their dyadic Dirac notation, right? So, so the S plus S minus is a projector. It takes B and creates B again, right? So I'm placing it there instead of S plus S minus. Now I'm going to look instead of central and side parts. I'm going to look on the box here, which practices orthogonality. So if we overlap two basis functions that do not coincide, what it will be? 0. So this term will be 0. At least one of these convolutions is 0. So 0. Next line, the beta times beta Bryant ket will be 1, but alpha times beta will be 0, right? So the whole thing can be neglected. Next one. There is a alpha times beta, it will be again 0. And only the last one has beta, 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 beta. So each of them get to 1, and the matrix element will be C beta star C beta. So this operator parses the probability that electron is in the state beta out of the whole state, right? So it completely removes alpha and answers us the CB, the absolute value squared. So probability to be in the state beta, and this is often called projection operator or projection. Next thing, that is not for some, but for everyone. Well, it is for some as well. The lower right of this box is an important definition. We will use it before we finish the class. So, the creation and annihilation operators for spin were designed later. First, in the community, people did design operators for magnetic projections, X, Y, and Z. But through intellectual effort, it was an analogy to harmonic oscillator. It was found that same as in the, I'm going back, I'm going to focus on myself because I will be literally hand waving. So in harmonic oscillator, we define annihilation operator as a superposition of position and momentum, right?
Mhm.
And we can roll back, express position operator as a summation of creation and annihilation, momentum as a subtraction. You see this, you remember this. Now, instead of position and momentum, we will have magnetization in X and Y direction. And if we add or subtract magnetization in X and Y direction, we will get S plus S minus operators. And we can roll back. If we add or subtract S plus S minus, we will get either X or Y magnetization. So this blue ugly box is a connection between abstract algebra of spin and real life of nuclear magnetic resonance and electronic paramagnetic resonance. Okay. And we still have the dictionary which stays correct. Now, and note for some, and it is a little more complicated than things that we considered before. Because of lack of time, it is very squeezed. One cannot just take it and tell it is a solution. It's only like a navigation for train to depart in the right direction.
I appreciate the in-sing slide for sound for the remainder of this lecture.
So, do you remember anything about angular momentum?
Gosh.
I wouldn't be offended if you don't, but thank you. So, one of the interesting things that we covered and discussed together, that if we find set of solutions, set of eigenstates for an operator, then any power of this operator will have the same set of eigensolutions. Like if we have solution for angular momentum first power, angular momentum squared, we'll have the same solutions. And we use it for two-dimensional rotator instead of solving for full angular momentum for Hamiltonian. Remember, instead of finding eigenvalues of Hamiltonian, we were finding eigenvalues of angular momentum projection on Z. Right?
Yeah. Right at me.
Because you were showing some mimics, everyone was like, I don't know that. Oh yeah, okay. So it is a standard way in dealing with angular momentum to discuss and to explore eigenvalues of both Z projection and angular momentum squared. And now suppose the following thing. Suppose we do have not one, but two spins, which is not a big wonder, like helium atom, right? or like H2 molecule, right? 2 spins. Then there will be 4 basis states: up, up, down, down, up, down, down, up, right? And we do have expansion coefficients in front of each of them. So these are on the two. One can express it as product of quantum state of each individual spin, then open brackets, and then we have this. How do you decide beta is up or beta is down? Beta is down. Okay. Down, down. Yeah, you should forgive my blind writing. Down, down, up, up, and the cross terms. Now, if one would process this problem as in a regular way and try to find eigenvalues of this 2 spin system for basis states and for solutions. So the most popular, most low energy, most low momentum solution will be as follows. So we are looking for 4 eigenvalues and 4 eigenvectors. And each eigenvector is a set of 4 numbers for coefficients in front of up, up, down, down, up, down, down, up. So the major solution of this problem, the eigenvector, will correspond to the following distribution of solutions: 0, 1 over square root of 2, minus square root of 2, and 0. Now you need to believe me, but we could spend another hour in deriving. And this will be connection to SEM's work. So this, oh yeah. So where this 0 coefficients stand in front of up and down, down, right? And this plus 1 over square root and minus 1 over square root stand in front of up, down, down, up.
Okay.
Okay. So if the computer allows it to skip slides, so we can skip first and last, and then write down the middle two. So first electron in alpha state, second electron in beta state, minus first electron in beta state, second in alpha state. So do you see this just symmetric mathematical construction? Now let's do reverse engineering and ask the question: determinant of which matrix will give the same answer? So
The one that's ones
yeah,
on the diagram.
like if we write down the symbols alpha 1, alpha 2, beta 1, beta 2 in form of matrix and take a determinant. So main diagonal minus off diagonal. So alpha 1, beta 2 minus beta 1, alpha 2.
If you just flip them. If you just
If one flips it, the answer will be the same. Right? And 1 square root of 2 in front. So instead of like making credit to Professor John Slater and his importance, one can just find the eigenvalues of two spin problems and arrive to the same conclusion.
and that's just the easier way to do mine. Okay.
Well, it's not a way to do your project. It's on the foundation explaining why this form of wave function is taken. Okay, done with comment for Sam. And yeah, I was planning to finish here on Friday, and now we need to, for 10 minutes, go to another section. So here is a connection between spin and magnetization. And here is the slide that I plan to arrive in in 10 minutes. So we need to have the solutions for projections Sx, Sy, and Z. For Sz, it will be 0 and it will not change. For the for Sx, it will be cosine of energy difference times T, for S sub y, it will be sine of energy difference times t. And sine and cosine of the same frequency are describing the circular motion, right? So how do we get to this point? On the board, you do see a couple of operators that we have already discussed. Do you recognize the commutation for oscillator and then anti-commutation for spin operator, or the subtraction of them will be not an integral motion. Now, here is the goal. The slides are quite short, and I'm complementing what is missing by words. So we do need the equation of motion for magnetic projections, Sx and Sy. Right? You have this motion along equatorial motion. Right? The expectation values of Sx and Sy can be obtained by adding and subtracting expectation values of S plus and S minus, right? You agree?
Very good.
At least doing protest. And now you do have in your repository Heisenberg equation of motion, right? So instead of finding a solution for wave function, one can find solution for operator and its expectation value. So we need to practice Heisenberg equation of motion for creation and annihilation operator. And we need to define the Hamiltonian and just make commutation. Okay. So this the Hamiltonian is as Melody knows, summation of this S plus and S plus S minus S plus, and one can put energies there. For simplicity, we can put that energies there are like plus and minus 1 or plus and minus 100. This is a little thing that we can always speak. Most important to play with operator algebra. Now, we do need to find the, by the way, this is the answer key to what we need to do. I'm just looking forward. Yes, so here is the little surprise quiz that I invite you to try. So we need to find the commutation between Hamiltonian and spin creation operator. There, you are free to try your own way. You are free to look into notes. Just do things in a reasonable way. There are two ways. One is to replace operators based on anti-commutation relation. Another one, just to convert everything into Dirac notation, identify the orthogonality relations. Okay. So let's work on it for maybe a minute, and then I'll look what you're doing and try to do it myself. So I just will see some. Okay, and you can edit it together.
Don't know if this is right.
Did you look into the notes on when you did it all yourself? Impressive.
I mean, It's just switching.
You're right, and has the party in the right direction.
Is the
Your trade is also going well.
Is the Hamiltonian the S plus and S minus minus
Yes.
or plus?
Minus. Minus. So let's focus camera on the class and ask Melody, can you briefly tell major idea that you're trying to do?
We're trying to do the commutation of this,
Like instruct others how you
Okay.
teach what to do.
like how to do the commutation.
You just explain what you're doing.
Okay, so what I did is I took the Hamiltonian, which is epsilon alpha 0, 0, epsilon beta, times the spin creation operator, which is 0, 0, 1, 0, and then you minus.
And then you do the math.
Yeah,
Okay, so main thing that maybe was not clear to everyone is that one needs to express Hamiltonian, this Hamiltonian in form of operators. And what Melody told that she took epsilon alpha, epsilon beta, but one can assume epsilon alpha equals 1, epsilon beta equals -1, just for simplicity, right? And then the Hamiltonian will be S plus S minus S minus S plus. Okay? Just to skip these factors to make things quicker. Now, this Hamiltonian has to be multiplied by this green things S plus at the back and at the bottom, and then process this equation with all available tools. Okay, let me have a look how things are. This. Minus times minus plus. Okay, you. Okay, so because we need to finish everything, please continue and I will collect, but I just practicing patience and show the answer key. Your grade will not suffer of what I'm showing, but we need to finish it within a minute because probably you need to go to another class. So the greenish thing comes from S plus, pink and cyan comes from Hamiltonian. Hamiltonian comes once here, another time there, right? When we convert the S plus, S minus, and S plus according to this dictionary, we'll get, see here, beta, beta, beta alpha, 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 beta, 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 alpha, beta, 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 alpha, alpha. Okay, and then you look there and identify the central part. If in the central part you have Brian Ket of beta beta, it will by orthogonality it is 1. If we have in the central area Brian Ket of alpha times beta, by orthogonality it will be 0. Or if it is alpha beta against 0. And here alpha alpha will be 1. Here you have one plus, one minus, here another minus. Minus times minus will be plus. And then we have on the first and last term, we skip this part here, so it will be beta alpha plus beta alpha. And beta alpha, now we convert back to the dictionary, it will be S plus, right? So we get in factor 2 because I did this simplification and skipped playing exactly with energies. But in fact, it should be without factor. So commutation of Hamiltonian with creation operator reproduces creation operator back. So operator commutes by commuting with Hamiltonian reproduces itself. When we plug it into the Heisenberg equation of motion, it means that it is a linear differential equation. Time derivative of S plus equals energy difference S plus. You see? And now we solve this differential equation. So ds plus over S plus will be energy difference times dt, which like log here, linear here. So S plus as function of time will be just exponential accumulating phase according to energy difference, right? And we can do the same trick for the S minus for annihilation operator, right? So it just accumulates energy into opposite direction. And now we appeal to our old buddy Euler, right? And we add together S plus and S minus and develop Sx and Sy projections. So if we add together the exponential, imaginary exponential rolling forward and rolling backwards, we get a cosine, right? If you subtract, you get a sine. And here how we get the sine and cosine for the Sx and Sy projection. If you don't have optical field, one can do a few more tricks to show that Sz projection doesn't change, which is basically same as Hamiltonian. And after looking on these three projections and getting back into the magnetization, you'll get cosine and sine will show this rotation. So if it is one electron, it will be infinitely long rotating. If it is an ensemble, since they rotate with different pace, there will be free induction decay. The length of this vector will get shorter and shorter, and it is what you see on your thing. So here is a verbal summary, and here let's stop share, and now it's finished. Oh yes, finish of the meeting. So